Okay, you hear that word force. What do you hear? What do you think? I tried to outweight you, but I can't do it. This is killing me. Syra, I'm just going to start talking to all of you one at a time. That's how we got to do it. Syra, the word force, what do you think of when you hear that word? Like pulling towards something, okay? Gernavin? Jewels. I'm going to write everything down, whether or not it's right or wrong. Iad, a push. Just hear it. Okay. Akash? Nothing, not a single thought enters your brain. You're just like, I'm here to absorb everything. Okay. So what's there already? Pull and a push, okay. Okay. I mean, there's other meanings of this word too. Liam, what are your thoughts with that word force? Okay. Something making, I'm going to run out of space. Something else move. Cool. Alexis. Motion. And Lena. Elements. Can you explain? I say the word force, you think of elements and air. Okay. Why? That's just what enters your brain. Cool. Works for me. Okay, let's talk about all these pieces. We've basically covered all of it. A force, a pulling towards something, a push towards, a push away or a pull towards something, making something else move. So typically when we use this word force, it is something applying something, lots of somethings, to something else. Do objects have to move if there's a force acting on them? I mean, could they move? They certainly could move. I come up to you. If I were to come up to you and push you or pull on your chair, you're probably going to move. But do you always have to? Why not? Can you give me an example, Lena? Oh, yeah, so if we chained the chair to the desk, bolted the desk to the floor, and then I pulled on your chair, but you're not moving, okay? So this is true sometimes. What kind of forces have to be applied then if this is going to happen? If you're going to move, what needs to be true? Good morning, Mr. Bell. Let's try that again. Good morning, Mr. Bell. Super duper, man. How are you? That's good. No. I haven't seen him for the better part of a month. Okay. See ya. Bye. Okay, if things are going to move, what needs to be true? You said so let's go back to your example of the desk. You're chaining your desk somehow. You're going to bolt your desk to the floor rather than actually chain the desk. Draw it. Here's your your desk, your artistic rendering. You're bolting that thing to the floor. Here's Lena. She has decided to chain her chair to the desk. And here I come. I want to pull this thing that way. She's not going to move. Why is she not moving? Lena, you said you're not moving because this thing's holding you there. Okay? So while I'm not pulling, the chain is just going to sit relaxed on the floor. I start pulling you. What's the chain going to do? It's going to tighten. And then all of a sudden, as it tightens, you're going to have a force that way. Your chain has to be holding back against me. But as soon as I stop pulling, so does the chain, right? So if I want you to move, I got to cut the chain. Or I have to pull hard enough. It's true. To either cause these bolts to rip out of the ground or the chain to break. I'm strong, but I'm not that strong. So if I want this to break, I'm not that strong. What needs to be true? The chain needs to be gone. And then what can you tell me about? Let's go back to this. I'll just put this in here. Right now, what is true about these two forces, the chain and me? In opposite directions. So when this is true, we've got language around this. If I'm pulling one, or if let's say I go up to, I don't know, Liam, for whatever reason, decides Alexis is going to come sit where Ryan normally sits. For whatever reason, he grabs her arm and starts to pull her this way. You said, no, Alexis stays with me. You pull that way. She's not going to move even though both of you are applying forces there. What is true about those forces? Yeah, they would have to be equal. And opposite. Which is kind of part of Newton's law, but we're really kind of working around, like, we're abusing one of Newton's laws really strongly here, but that's okay. We'll come back and we'll fix it later. These forces have to be equal and opposite. When things are equal and opposite, we've got a B word that we use for that. I know you're German, so I don't know what letter your word starts with. In English, it starts with a B. The forces are the what? Yeah, balance. So if forces are balanced, there's no motion. You can push as hard as you want on something. I'm applying a force to the wall right now. It's not moving because there's a force, the rebar in here. The stress is on the wall. I'm not going to push the wall down today. Okay? They're balanced. They have to be. So in the same situation, it's true. They're balanced. If I cut the chain, now these forces are no longer equal and opposite. The forces are what prefix can we add to this? Unbalanced. Lena wasn't moving before. I am applying a an unbalanced force on Lena. What you start to move, so what must be true? Your VI was 0. Now you're moving. VF equals not 0. What had to have happened? But if VI is 0, initially you're not moving, you're sitting there. I come up behind you and I go, refund your chair. Now you're moving backwards. What have I caused? Yeah. What else have I caused? I'm looking for a different buzzword from chapter 2. Starts with an A. Yeah. An unbalanced force is going to cause an acceleration. You guys have forces acting on you right now. We'll say that gravity is acting down on you. But none of you are sliding towards the center of the earth. Why? What's holding you up? You're not on the ground right now. there are plates down there far enough. What's holding you directly up right now? Sort of. The chair you're sitting on. So there's a force on you from the chair. There's a force on the chair from the floor. There's a force on the floor from, right? So immediately it's the chair and gravity are the ones that are balancing you out right now. So we've got a pull towards and a push away. Something making something else move, or trying to at the very least. Motion is true in some cases. Motion is true when this happens, and your forces are unbalanced. Very curious why your brain really jumps to elements in there, but that's okay. Joules. Let's talk about joules. Joules would be units, right? They're units of something. What are they units for? And are they the right units for force? Well, Newton's laws were all developed by a gentleman named Isaac Newton. He had a pretty significant impact on exactly this whole area of physics that we're about to talk now. We call it Newtonian physics. There's non-Newtonian physics, and then there's Newtonian physics, and that's what we're going to look at here today, or this probably next 3 weeks. And so because it's all about Newtonian physics, we do the guy solid, and we name it after him. Joule was a French physicist. His involvement in the world of physics was not this. He gets his own unit later on. We'll talk about joules. But he had nothing to do with this. So the only thing that actually doesn't belong, well, I mean, I still don't know how elements in air are going to work in here, but that's okay. Let's talk about these. So because so much of this section, it's based on Newton's 3 fundamental laws. So we say, we've given the guy a solid, we say the units of force are newtons. We give that a big capital letter N. But like so many things in physics, to get this unit of the Newton, there are other fundamental base units. Like part of the whole first unit we did, we talked about measurement. I gave you, we watched a Veritasum on where these units come from, how we define some of these units. So the Newton doesn't come from nowhere. The Newton is based on another set of units. We're gonna make an equation here for this unbalanced forces equals an acceleration. So there is a direct relationship between an unbalanced force, which I'm going to call big F. This is only true when this is unbalanced. But there is something else that's going to impact the acceleration here. What is it? Come sit over here. So, I'm going to erase on the desk. Apply a force on the eraser. It moves. There's an unbalanced force. I flick the thing. Okay. You're not. Okay. Here I am. He did not go flying the same way. Why? Go higher mass. So the acceleration and the force are going to be impacted by the mass of the object. Sweet. So this actually is the equation. It's a very simple equation. It's a very direct equation. F equals ma. Perhaps you've seen this before. Now, this capital letter F has these units here of newtons. But mass and acceleration have units of their own. Mass's units are kilograms. And the units for acceleration are meters per second squared. Good. So forces we define them to be newtons, but they're actually based on this idea that that a force is equal to a mass times an acceleration. So the Newton must be equal to a kilogram meter per second squared. So these are the fundamental SI units that the Newton is based on. 1 Newton is 1 kilogram meter per second squared. Which means we can start redefining mass too. We can go back the other way. We say a kilogram is equal to a Newton second squared per meter. But you're not going to go into the doctor's office and quote your mass that way. But all of these can be, we can start moving some of these units around and start redefining stuff. There are 4 fundamental forces that make up all the forces in the universe. Ooh, what are they? What do you think? What do you know? Gravity is the big one. Gravity is number 1. And I'll say it now and then come back to it later. Maybe. It might be a force between masses. Depending on the kind of physics that you're looking at, gravity is either a force or gravity is not a force. And that should make you uncomfortable for reasons you don't know yet. In Newtonian physics, a completely fantastic explanation for gravity is that the more mass you have, the larger force you exert on things around you. So the Earth is pulling you down. We've looked at this already. You guys found the acceleration due to gravity. If gravity causes an acceleration, it must be applying a force to you, according to Newton. If there's an acceleration, there's an unbalanced force. Good morning here, Day. You need the dynamics package from underneath the TV there. It should be on the back. It should say dynamics on the cover. But if you're Einstein, gravity is no longer a force. We'll look at that when we get to, when we talk about gravity in more detail. Okay, that's the first one. There are 3 more. Do I have any chemists in the room? Anyone also taking chemistry? Okay. There are 2 here related to the study of chemistry. You guys talked about forces at all? No, not really. Chem 11? Are you in chem right now? What have you done in chemistry so far? Oh, you've been doing that stoichiometry stuff. Yeah, that's what you've been doing. Okay, you haven't talked about it yet. Okay, let's talk about let's chemistry in science 10. How do atoms and molecules, how are they together? How is, like water, for example, how does water stick together? Or stick to itself? Bonds in English. Yeah, here day. Charges. You need, so a whole class of compounds are held together by the fact that they're charged. Okay? So the second fundamental force is electromagnetic. This is the force, again, maybe, between charged objects. I really should have made the box bigger. And those are the big 2 that you guys should all be intimately familiar with. Gravity, you have experienced. Electromagnetic force, you've experienced. If you've never played with a magnet, you had a deprived childhood. I'm really sorry to say that. If you've never, dragged your feet along the ground and shocked someone, you need to do this. Preferably not to me. But as a kid, I did this to my mom all the time. We walk around Costco. Costco is great for this. You drag your feet on the floor and you sneak up behind her and you shock your mom. Electromagnetic forces. So those are the 2 that you guys should be familiar with. The third and the fourth, again, depending on how far you've studied into chemistry, you're going to experience these at some point. One of them is called the strong force. Again, not super creative names here. There's a strong force and there's a weak force. Are the other 2 fundamental forces that I don't necessarily expect you to have had any sort of interaction with. And when we say strong force and weak force, the strong and weak forces, even the weak force is not weak. It is a very strong force. These two forces are the forces that actually bind atoms to themselves. So atoms are made up of smaller parts. That is what the strong force does. It holds atoms together. So atoms are made up of something called quarks. And for those quarks to stick together, there has to be a force on them. We call that force the strong force, or fully, if I had a slightly more space here, I'd write the full name. It is the strong nuclear force. Holds the quarks together to make an atom, or to make a proton a proton. I shouldn't say atoms here. I should have said atomic particles, but that's okay. So like to hold a proton together, you need a force that binds the three quarks together. And the weak force holds nuclei together. So this is the force that causes a proton and a neutron to stick together to form the atom. So I should really change this first one. This should be an atomic particle. So the strong force holds the pieces that make a proton to make a proton, the pieces that make a neutron to make a neutron. The weak force holds the protons and the neutrons together. That force is very, very strong. To break apart things held together by the strong force, we built something called the Large Hadron Collider. We accelerate objects to near the speed of light and then smash them into each other. That's how this happens. That's how we break this. One sec here, Dave. The weak force is everything that's related to atomic energy, the atomic bomb. All that energy that gets released when we're able to split these atoms is directly related to this weak force. Yeah, here, Dave. This one, the weak force. It's related to that one. And again, weak force it's a fundamentally very strong force. So these are the four fundamental ones. Gravity, depending if you're Newton or Einstein, may or may not be a force. The electromagnetic force, and then the strong and weak. Those are the four fundamentals. And from those four, everything else gets built. There are many forces that act that we will identify in our world. You've said one already. Let's bring gravity over here. As far as we're concerned, we're going to treat gravity like a force, and we're going to call it F sub G. When I say sub, I'm a little subscript down here. Fg. And this is the force that acts between masses. We're going to look at universal gravitation in this chapter, and we're going to figure out what the gravitational attraction between you and the person sitting next to you is. It's not hard to do. We're going to do it. It's going to be great. We already talked about it. So gravity pulls you down. There has to be, you guys aren't falling towards the center of the earth, so there has to be some upward force on you, whether you're sitting or standing or lying on the ground, whatever. Something is holding you up from making your way to the center of the earth. That force has a name. We call it a normal force. And that's going to be F subscript big N. And again, this word normal doesn't mean probably what you think it means. Normal, there is a mathematical idea built into that name. In math, does anyone know? I don't, maybe Gernava might be the only one who's seen this, so I think IB is the only place this language is going to show up. If things are normal to each other mathematically, does any of you know what that means? Maybe Lena, because she learned math in Germany, and Germans do more than we do in our high school curriculum. If things are normal mathematically, what does that mean? Any of you know? So you guys are hard to peg because either you know it and don't want to say it, or you don't actually know it. Lena, have you heard? You would say it if you knew it. Gernavin, have you seen it? IB, year one? Because I don't think any of the rest of you would have. So if things are mathematically normal to each other, it means they're perpendicular. Perpendicular means they meet at 90 degrees. So a normal force acts perpendicular to a surface. And that word perpendicular, just, some of you haven't seen it since middle school, means it acts at 90 degrees. So your chair isn't totally smooth. So the force on you isn't perfectly up everywhere on that chair. The force is going to be perpendicular to whatever the surface is. So on a flat desk, it will be straight up. But if you angle the desk, that normal force is going to get angled too. We're going to talk about that in a lot of detail. It has some interesting implications. So we've got gravity, we've got something called a normal force. Now there are some more here that you will be familiar with. Sorry? What do you call it in German? Nice. That's a cooler word. Okay, what other forces act? What other forces are you familiar with? Simple forces. I'm not asking you to come up with strong and weak nuclear forces. Forces you experience day to day. Yeah. What do you mean by resistance? If you're trying to move something, there's going to be resistance. Okay. We have a name for that. Starts with, if I'm understanding you correctly, it starts with an F. Yeah, your friction force. And friction we're going to label as F with a subscript of little f. Friction opposes motion. Does anyone know where friction comes from? Yeah, it depends on the surfaces. So if you're dragging two objects over top of each other, they are going to have a different kind of friction as if you had changed one of those two objects. For example, if you're dragging a steel block over top of this floor versus a rubber block over top of this floor, the friction you're going to experience is going to change. Why? What property of those two objects is, what are the properties of those two objects that are either increasing or decreasing friction? Okay, it's more bumpy. Okay, so friction, yes, it opposes motion, and it is caused by the interlocking of rough surfaces sliding. It doesn't really matter how smooth you try to make something. There's always going to be a degree of friction there, unless you can insert something to fill in the interlocking of rough surfaces. We do that all the time. We lubricate stuff. Bearings, you have to put grease in there, otherwise the metal's going to grind on the metal. On ice, ice is nearly frictionless. This is the closest thing that you guys will probably experience day to day that is frictionless. Why? Because when you step on ice, what happens? Wait, but why? Why do you fall? Yeah, but something happens that causes that. Yeah, here it is. Well, the floor here is clearly flat too, but if I push you here, you're not going to fall down or slide to the wall. There's going to be more bumps than the ice will? True, but there is something that gets added to the ice when you step down on it. Yeah, that. It melts a little bit. A microscopic amount of water gets in there, and as soon as the water gets in there between your feet and the floor, that's what reduces friction to almost zero. It's that little layer of water that forms between you and the ground. It fills in these interlocking rough surfaces. We're going to do a whole lesson on friction. Okay, cool. What else? You said resistance. Did you also mean a different kind of resistance here today? You brought it up several other times. There's another kind of resistance. if I throw you out of a plane, what other kind of resistance are you going to experience? The air resistance. You guys have talked about it a lot. Air resistance. This, we're going to put an asterisk next to this. We are not going to treat air resistance the way it needs to be treated. Another word for air resistance is drag, and we're going to call this F air. We are going to talk about it, but we are not going to treat it properly. I've said it a few times. We just don't have the mathematical skills to deal with air resistance. Air resistance depends on a lot of things. It depends on the shape of the object. It depends on how fast the thing's moving. Air resistance is really, really hard. We're going to abuse it a little bit, kind of talk about it on the side, and then ignore it. But this is the force of air molecules impacting moving objects. There are a few more here. What other forces have you experienced in your life? Yeah, here today? Sorry? I'm going to put this down here right at the bottom and we're going to name that an applied force. It isn't quite what you're describing, but this is the closest thing to it. We're going to call it F subscript big A, and this is a catch-all force. If you don't know what the force is, but you know there is one causing something else to move, we say you've got an applied force, and then we go and figure out what that applied force is. Sometimes we need to, sometimes it's obvious. If you're pushing something, you are the applied force. But for example, if we talk about how things move, okay? I'm going to go for a walk, shall I? How am I walking forward? What is causing? I'm accelerating this way. So there has to be some force on me this way. What is it? Okay, we don't know what it is, so sure, we can call it applied force. But what is it? I don't want to keep, I'm not going to run. Okay, so what are my legs doing? I'm moving the force. So I step forward, I shift my weight. But what is causing me to go this way? If I did this on ice, it would look like this. When Michael Jackson does it, he does this. Except he's dead, but he did this. But what's causing me to move the way that I'm moving? How am I able to move that way? On ice, it would just look like this. That's a huge hint. What's causing me to move this way? Yes, actually, the applied force that's causing me to move forward is actually a friction force. So, but if friction opposes motion and I'm moving this way, then how is friction causing me to move forward? What's friction doing? Yeah, when I push my foot, when I shift my weight forward, my foot wants to go which way? Backwards. So I'm moving that way, so something has to be causing me to go that way. So yeah, it's friction between my foot and the floor. So we can call it an applied force until we actually nail down what it is. So it's not actually an applied force, it's friction acting on me, pushing me forward. Cool. So you got your applied force, it's the catch-all. Sometimes it'll be you, sometimes it'll be something more specific. Okay, I've got three more that we've discussed in the past with I've discussed in the past with other classes. Let's see if you guys can find them. Sorry? Ooh, that's not actually a force, but we're going to talk about that in physics 12. For those of you who didn't hear what Liam just said, you said centrifugal? Centrifugal? That one gets abused like crazy in popular culture. What is it? Can you want to describe what you think it is? Yep. You just heard about it. In what context? Okay, so something spins. The force on that object is which way? Is it though? It's got to be center seeking. So this is the common misconception where you have a centrifugal force and the spinning object, and it's the same. You experienced this. Okay, fine. Now I have to demonstrate it. I'll demonstrate it with my extension cord here because it's nice and easy because I don't have a bucket. So what you're describing is this. I spin this. I'm not going to let it go. You're not going to get hit. I don't even think I could reach you on it. I let it a little bit further. So you're talking about the force on the end of this rope. The bucket there, you say, would be an outward force. Because if I let this thing go, it's going to fly away from me in some direction. Yeah. That isn't actually a force. And you're at the risk of wrecking a whole unit in Physics 11. Physics 12. We don't do circular motion in 11. We save circular motion to 12. Go back to this for a second. The object isn't flying away from me now. So which direction does the force actually have to be at? So when objects are moving in a circle, there's an inward force, which we call centripetal, center seeking. And as soon as I let this thing go, all I've done is I've cut off that center seeking force. So that just is going to allow this thing to fly the way it wants to. So that inward force is what causes it to stay in a circle. Cutting that off is what's going to allow it to go out. So that outward seeking force is what you experience. You experience that because of inertia, which we talked about already. And we're going to talk about again. So good guess, but not quite. And even then, that centripetal force is going to change. What that inward force is going to change depending on what object I use. In this case, I was using an extension cord. Extension cord is effectively a rope. What force is going to act on ropes? We have a name for it. You've almost certainly heard it before. It starts with a T. Tension. There's only one E in tension. T-E-N-S-I-O-N. Tension. We're going to call that F subscript big T. This is the force. I'll use the word associated with ropes, chains, etc. when pulling. We call it a tension force. And there's one more. I pulled out a rubber band from a box of rubber bands that I have that you guys are going to use later when you build your bungees. Are you afraid of the rubber band right now? You shouldn't be. Alexis, how do you feel about the rubber band now? A little more concerned? Why? But if I threw it at you, that would be different. There, I threw it at you. Were you afraid of it while I was throwing it at you? No, but if you pull it back and point it at me, now I'm more concerned. Why am I more concerned? Why? So you're applying a force backwards. It's not tension in that thing. We have another name for it. You have given it potential energy. There's a particular kind of potential energy. What kind of potential energy? Elastic. The beauty of those things, they are simple objects, but they are fantastically powerful little objects because lots of objects inherently have what's called a restoring force. We give that name elasticity. And we're going to call that an elastic force, elastic. And we're going to call that F subscript big E. We like elastic objects. We can make elastic objects do a bunch of stuff. As Gernavin said, we can use it to store potential energy, which is the whole purpose behind a bungee, which we're going to do next chapter? Next chapter. In this chapter, we talk about it as a restoring force in a stretched object. That's how we're going to call it. Restoring force in a stretched object. And those, it can be quite a powerful restoring force. That's what causes it. When Alexis points it at you and she pulls back, when all she has to do is let go. She's not projecting the thing forward. She just lets go. And the fact that that bungee wants to collapse back in on itself, holding it at one end, go for it, shoot it at the board. The reason it flew is like it did is because the back end wants to be restored to its original shape. And so it slides forward, and then its inertia carries the whole thing forward. That's the beauty of those little wooden, I don't know if you've seen them, but often if you go to trade shows or like a home show, maybe you guys haven't done any of this. My dad dragged me to all these when I was younger. But there were like the little, people would make little wooden elastic band guns. There's a gear on them, and you load all of the elastic bands up, and you just pull the trigger, and it just lock one at a time going forward. It's this. The elastic restoring force in all of those rubber bands is what causes these things to shoot forward. So these are generally the ones that we're going to talk about. There's another one that you've experienced if you've ever been in water. We call it buoyancy. Buoyancy. Or a buoyant force. We're not going to talk about it in a lot of detail, but it's another force. Water doesn't do a great job of holding you up on its own. Like, it doesn't have a normal force associated with it, but you can float depending on your density, and we call that buoyancy. Sorry? Yeah, go for it. All of that or just the one word? But buoyancy? Okay. I could translate it for you too. Buoyancy. I don't even know how to pronounce it. Auftrieb. Okay. Yes, my German with an English accent is terrible. It's true. Okay, so you're cool with the concept now? Okay. These are the forces. We're going to talk about a bunch of these. We've got whole lessons dedicated to some of these. But before we do that, I want to introduce you to a certain kind of notation that we use when we talk about forces. These are free body diagrams. Now, in the second chapter, kinematics, I encouraged you from time to time that it would be useful to draw diagrams to get you a picture of what's going on. Now, all of a sudden, the free body diagrams are going to become mandatory. Drawing a diagram for this is going to be an absolute requirement of what's going on here, because there's no real good way to identify the forces on an object unless you sit down and draw them out. So we draw what are called free body diagrams. To use and keep track of all the forces involved in a particular situation or problem, we're going to use what's called a free body diagram, or FBD. So in kinematics, when I was marking you on stuff, I said I want it exactly this way. I want you to write out what you know. I want you to write down the equation that you're going to use. I want you to fill in the equation. I want you to give me an answer. And sometimes you have to interpret it. Is the plane going to crash? Yes or no? It's not always no, Lena. But usually people are going to die. It's true. The added step to this now in dynamics is the free body diagram. You've got to include it. So if a box is being pushed across a rough floor at a constant velocity, a free body diagram is going to look like this. All you draw for a free body diagram is the object. And a box is really straightforward. We can draw it as a square. Let's toss the ground in here. There are words in the problem that give us, just like in kinematics, there's an implication to the words that we choose to use to describe the problem. What are some of the words here that are flagging us? Yeah, here today. Constant velocity. Okay, what does constant velocity imply? Cool. So if there's a constant velocity, that means you have a balanced set of forces. Balanced forces. The other implication here is that if you have forces that are balanced and you have a velocity that is constant, your acceleration is going to be equal to 0. So there's two things we pull out of those words. Constant velocity means the forces are balanced, acceleration is 0. Cool. There's another word here. There's two more you could technically argue. Pushed and rough. Pushed implies the existence of what kind of force? An applied force. And rough implies the existence of what other force? Friction. Cool, so let's draw them. If it's being pushed across the rough floor, generally when we push things across the floor, we default to that direction being to the right. So let's say that there's an applied force this way. There's our applied force, and we label the thing. If it's being pushed to the right, then friction's acting the other way, yeah. So that's going to be my force of friction. Are those the only two? And technically speaking, if the forces are balanced and the acceleration is equal to 0, these arrows should actually be the same length. These two forces we know have to be equal and opposite because constant velocity. But there's two more forces acting on this object. It's sitting on the floor. So that floor is going to be exerting what kind of force on it? It's in that orange list up at the top. Actually, it's blue. Yeah? Gernavin? Gravity's which way? Down. And gravity exists because you're on the Earth. But the object's not falling to the center of the Earth because it's sitting on the floor, and that floor then must be exerting the other blue force, the normal force. And normal is not always straight up, which you're going to see here when we do look at inclines. It's always perpendicular to whatever surface is. If the floor is that way, then straight up just happens to be perpendicular. Cool. Looks very similar, but in example 2, we have a hockey player gliding on a frictionless ice at a constant velocity. So let's draw the ice. The hockey player is a box. What forces are acting on the hockey player? What words in there give us information to either include or exclude? Here, Dave, you've put your hand up and down like a couple times now. Sorry? Exists or does not exist? Based on what word in the description of the problem? What part of skating is the glide? Have you skated before? I'm terrible at it. You've skated? Okay. So at what point in skating are you gliding? When you just let go of yourself, after you've pushed. So gliding actually, not only does it not do what you want it to do, it does the exact opposite of what you're suggesting it does. If you're gliding, that word implies no FA, no applied force. Because it's after the push. The push has happened at some point in the past, you're done. There's no longer an applied force acting on you if you're gliding. Cool. Frictionless ice. I mean, that word is pretty straightforward. No friction. And again, constant velocity implies that whatever forces do exist are balanced, and that A is equal to 0. So there's no applied force, there's no friction, but the object is moving with no acceleration. So what are the forces that are on our hockey player box? Gravity and there has to be a normal force. And that's it. Even though our object is moving to the right, these are the only two forces acting on it because there's no friction, there's no applied force. These are balanced, acceleration is equal to 0, even though we have movement. Because at some point in the past, our hockey player either got pushed or pushed off the ice his or herself. So as far as the free body diagram goes, these green ones are the only ones you have to include. Questions, comments, concerns so far? Okay, cool. There are none. Flip the page. I would like you to draw for me 8. See what you, pencil would be preferred for reasons that are going to become obvious in a second. And maybe do it off to the left so that if and when you're not, totally correct, you've got some space that we can draw a correct one. I want you to see if you can interpret the description in all 8 of these and draw free body diagrams. Feel free to discuss with the people sitting around you. Draw me some free body diagrams on your market cycle. You don't have to be an artist. If you'd like to be an artist, you can. If you don't want to be an artist, then circles and boxes are just fine. Yeah. If you are in contact with a surface at any time and you're not following through it, the fact that it's holding you up is the normal force. Yes. Anytime you have an object impacting a surface, you call that normal force. So even if I'm standing here leaning against the wall, any surface doesn't have to be flat. I'm leaning against the wall. The force that's holding me up off the wall is a normal force because I'm not following it. Anytime you're in touch with the surface, that's a fact. And it's always perpendicular to the surface. Yeah, if you're on the wall and on the ground, yeah, that'd be 2. Every surface you touch has another normal force. Were you pure math? Or did you do? Oh, okay. You were also math PE. That was passive PE last time. Generated by the engines as well as a lift force by the wings. Assumes level. Unless it specifies otherwise, assume level. You know what? It doesn't actually matter. It won't change the free body diagram. Yeah, so in this case, the applied force is U. Friction is on the ground holding you back, or holding the pencil back. In the plane, the label is also going to be a normal force of gravity. Plane, but you have to label those forces. Don't just show me arrows, actually label them what they are. What is this force? Yeah, FA from the engine. What's this force? Why is there an upward force? better not be, otherwise it's not flying anymore. So what's causing that upward force? It's the lake. It tells you in the wording of the problem. Actually says it. There's lift. So that upward force is a lift. Is lift. F lift. Yeah. That's what's keeping the plane in the air. There's no normal force. And in this case, again, it's not, friction only exists between two objects that are sliding. The plane is not sliding, so we can call that air. Because you move the plane is on Earth, yeah, you don't have it. That labeling it properly is as important as throwing arrows down. I've never actually seen Primer, but I've seen the rest of them. Normal. Okay. Some of you are making your free body diagrams a little more elaborate than it's. I'm never going to. Don't hear me say this as a criticism. It's more elaborate than it needs to be. If you don't want to get super artistic, feel free to not. But I'm never going to criticize too much of artistic artistry. Football is moving upwards towards its peak after having been booted by the punter. How the football movement being punted. The punter's keeping the straight in the air, that's doing his job. But again, does that change the diagram? And it tells you that there's a specific point that tells you that the football that moving at its peak. Does it matter? Doesn't matter where in the arc the football is. It's such a simple task, but it is wildly complicated. You guys are not used to thinking about this stuff that way. And so much of Physics 11 is just deconstructing what you think you know about how the world works and building it up with arrows and numbers.
Skydiver?
Yep.
Someone who jumps out of the plane and tries to glide in the air for as long as possible. So there's technically implied force in the direction of gliding as it jumps out.
Is there an applied force?
That's what I'm asking. Like, they probably didn't just like fall, because that's not diving. When I go like this,
Well, it is diving.
it just says they're falling.
But so a skydiver is anyone who's jumped out of a plane.
So there's just jump.
They could just do this. Skydiver just means you have left a plane above the ground. However you left it, doesn't matter how you leave the plane. Is the person currently in the middle of a jump? Like this. No. They are flying through the air. So even though there may have been, this is where you guys have to, this is what I said before. You have to separate out what you know, what you think you know about how the world works. Just because there may have been an applied force in the past, is there an applied force right now as you draw the free body diagram? applied force doesn't matter. It's the same thing as the football question. Was there an applied force at some point in the past to cause the football to be where it is? Yes. But is there an applied force acting on the football as it flies through the air? No. Just because an applied force caused a situation to happen doesn't mean it's acting right now. The applied force only acted for an instant as the person's foot came in contact with the ball. And then as the ball leaves, the applied force is gone. Once you're done, I want you to compare with the person sitting beside you. Force you to talk. Compare with someone sitting around you. Because I'm noticing some differences in these drawings. That won't be right. It's Princess Spider-Man, I love it. Yeah, man. These glasses. Did. It was interesting because he did one question totally correctly in the section. I don't know all the questions in that same section. But it was the exact same set of skills. You'll get it back. Follow the map. You won't get it back today, unfortunately. Even though they were the exact same stuff. We'll use it as it's called. So this is not an exhaustive list. It's just the common ones. Like I have specific lessons on friction, on normal, on gravity, on tension, on elastic. We have specific lessons on those. Lift is this if the question inserts an added one, use it as it's described. But I don't have anything on lift. We're not going to do a lesson on lift forces, but we're going to do specific lessons on all of it. Discuss your drawings. Your drawings are not the same. You can't both be right. Okay. We got one more. The plane. Normal forces only exist when you're in contact with the surface. The only time the plane is going to experience a normal force is when it's on ground. Or aircraft carrier. Sorry, was that a hand or were you just brushing your head? Okay, let's draw some of these. You guys are almost, if you're not totally done, I know you're almost done. Let's discuss these things. There's 8 minutes left. You're not going to have any homework from me. We're just going to talk about the rest of this and we're going to call it. So, a book resting on the tabletop. There's my book. What forces are acting on the book at rest on a table? Here, Dane. Gravity, down. And if the book is on a tabletop, there also has to be a normal force straight up, presumably. We're making some assumptions here. We're assuming it is a well-crafted table. Means it's not askew. Okay. Let's just go left to right. A rightward force is applied to a book in order to accelerate it across a desk. Again, lots of implication here. We've got a book. What are the forces acting on the book? We've got gravity, because presumably the book is on the earth. If it's on a desk, there's also a normal force. Assume that the desk is well constructed. Normal force is straight up. What else? An applied force, let's say it's to the right. We don't know, so let's assume. Tension. The other thing, what's the other thing? Again, we're making friction. We're making an assumption, but a normal book on a normal desk, and I'm using normal, not perpendicular, I'm using it to mean a common book on a common desk is going to experience friction opposite to the direction of motion. And what do we know to be true about FA and FF? Cool. Love it. The applied force has to be bigger than the force of friction if it's accelerating due to the applied force. Love it. Number 2. A girl sits on a swing that is attached to the frame by 2 ropes. So there's a few ways you can draw this. Some of you got very artistic, and that's awesome. Don't let the artistry impact you negatively. A girl sits on a swing that is attached to the frame by 2 ropes. There's a couple ways you can draw this. If we're talking about just the girl, what forces, so let's draw it 2 ways. I've got just the girl and girl on swing, which sounds like a really bad painting. If we're drawing just the girl, what forces are on the girl? Gravity down. And what else is acting on the girl? A normal force. She's sitting on a seat. If we're talking about just the girl, that's it. If we're talking about girl on the swing, we actually have to draw the rest of it. There's the swing. If we include this as part of our drawing, what forces exist? The ones we're going to add are tension. Where are the tension forces? On each side, acting which way? Gravity acts down on the girl, presumably on the swing seat as well. Normal force is acting up on the girl from the swing seat. If the seat is not falling towards the ground, which way does tension have to be acting? Upwards. Tension is the reason that the seat itself isn't flying towards the ground. Skydiver. What is acting on the skydiver? Gravity and air resistance. Fg down, F air up. And what do we know about these 2 forces? Here they? They're balanced, so they are equal and opposite. You bet. We have a name for this. This is called terminal velocity. And it is the maximum speed that you will reach as a skydiver. And it changes depending on how you orient yourself. This is how skydivers catch each other. If one jumps out of the plane and looks like this, and another one jumps out of the plane and goes head first, the person going head first is going to have a higher terminal velocity. They have less drag on them, less air resistance. And then to slow yourself up, you just go flat and big. Okay, an egg falling, free falling from a nest in a tree. That's really sad. Let's assume that the egg survives the impact with the ground. As it's falling, here's our egg. What is, if we're told to neglect air resistance, what forces are acting on the egg? Gravity. Anything else? Here today? Neglect or ignore air resistance. So there's only gravity. Cool. Number 7, a football is moving upwards towards its peak. There's our football. What forces are acting on the football? Gravity. Anything else? I know some of you wanted to draw an applied force, but is there an applied force acting right now? No. This comes back to the projectile motion stuff. An object that is considered a projectile is only under the influence of gravity. Akash, which one? Number 4, a plane flies at constant velocity. Ooh, let's actually sort of draw a plane. Okay, it's got a tail, it's got some wings. It's my poor drawing of a plane. What forces are acting on the plane? Gravity. What else? Which way? Based on my drawing of the plane. Yeah, forward. Planes don't go backwards very well. That was unexpected. I thought I had another 2 minutes. Okay, that's what the drawing should look like. I'll show you the last one tomorrow. You have no homework from me. I won't show you tomorrow. I'll show you on Monday. If you didn't write the test yesterday, you have to come in tomorrow to write it. Those of you I will see. Anybody else, I will see you on Monday. Have a super duper weekend. We'll see you later. Welcome to Dynamics.